In this video, we will talk about path integrals. It defines a distribution over the stochastic path. So far, we looked at the homograph forward and backward equations. These PDEs describe how probability densities evolve over time and how the expectation evolves at the population level. These are very powerful tools, but they have limitations because the probability density function only tells us the distribution at a snapshot. But stochastic processes are really about random paths. So let me give you an example to start. This example is about stock trading. Let's say I have a friend who is really into Tesla stock. Let's say that the Tesla stock is trading at $400 right now. So his strategy is that he will sell the stock when it reaches $1,000. Otherwise, he will hold it for a year. Then my friend coming to us, knowing that we are very good at math, he asked us to evaluate his strategy. So there are a few questions he's interested in. For example, what is the expected return after a year? And he's interested in when the Tesla stock will reach $1,000. But the time to reach $1,000 is random. So you can frame this question as, what is the expected time to reach $1,000? And there can be many other questions associated with this strategy. Although this problem appears to be very straightforward, the point I want to make is that just using the Fokker-Planck equation, just having a probability density function is not enough to answer these questions. And let's try to understand why. So the solution to the Fokker-Planck equation only tells us the probability density at the endpoint. So let's say that this is the endpoint at t equals to 1 year. And for the starting point, we have the $400 stock. And let's say that his target for $1,000 is here. So the challenge here is that this trading strategy is path dependent. So basically, if the stock reaches $1,000 early, then my friend will sell the stock. And it doesn't matter what is the price of the Tesla stock after a year. So basically, the $1,000 here is acting as an absorption bond. And once the stock reaches $1,000, this process stops. But with the Fokker-Planck equation, we only know the distribution of the stock price at t equals to 1 year. It does not care about the intermediate value of the stock price. So that's why for this trading strategy, it is not enough, because the intermediate value of the stock price matters. So this leads to a natural question. Can we assign probability to path? This is really the motivation behind the path integral. And in fact, this is very much related to the stochastic simulation that we talked before. So the idea here is that if we can assign probabilities to path, then we can solve this problem. And for this particular example here, it's actually related to the first passage time problem. And we'll look at the first passage time of the Brownian motion later in this video. Okay, so before we get into the path integral, let's just look at the stochastic simulation that we talked about before. So let's recall the stochastic simulation. So let's start with a process given by the stochastic differential equation. So the idea is that we can break time into intervals of delta t. And then we can use the stochastic differential equation to gradually generate a path using the increments. So the difference between the increments, let's call that delta xi. It follows a Gaussian distribution. And basically, we can just repetitively sample values from this Gaussian to generate a stochastic path. Here, let me just use the superscript to denote a path. And the main idea is that we can generate this path m times. And that will form a population. So the key conceptual idea here is that we think these are the samples from a probability distribution of the path. So this is actually more powerful than the probability density function we dealt with in the PDE, because the density function only tells us the probability at one specific time point. But with this stochastic simulation, we can obtain the entire history of the stochastic processes, which is at the path level. Then with this stochastic simulation, we can easily help our friend to evaluate his trading strategy. So we can just truncate this simulated path at $1,000. So basically, after we generate a simulation, the path stops once it reaches $1,000. And that is the distribution our friend is really interested in. Okay, so now we are ready for the idea of the path integral, which is really about assigning the probability to the path. The stochastic simulation is a good starting point, but it only samples at finite points. We have n time points where the stochastic processes is sampled. The stochastic process, however, is continuous. So the key idea of the path integral is really about what happens as n goes to infinity. And when we sample at infinite time point, we obtain a continuous path. Okay, so let's write this down as the equations. And just for the simplicity, we're just going to consider the vanilla Brownian motion from now on. But the formulation of the path integral can easily be extended into the general framework given a stochastic differential equation. Basically, we can consider the limit of the finite time steps. So the difference is given by a normal distribution with mean 0 and variance delta t. So for the probability of the path, let's just write out the finite version of it, then take the limit as n goes to infinity. So that is given by the product of the Gaussian densities. So we can just imagine that we are sample at infinite amount of time points for the stochastic simulation. And now let's simplify this expression a little bit. We can merge the first term. Then for the second term, this product exponential can be converted into a sum. And we need to take the limit as n goes to infinity. So notice that the first term is not depending on the path because it has nothing to do with x. So it just means that this probability is proportional to the second term. And if we look at this sum inside the exponential, it actually looks like an integral when we take the limit. So basically, when we have some function f of t with a range from 0 to capital T, then we can break the time into n intervals from t0 to tn. So each interval will have a length delta t, which means that delta t times n equals to capital T. Then we can just approximate this integral with a sum. This is a Riemann integral formula. We can just match the form and replace the sum with an integral. Then we will have xi plus 1 minus xi over delta t squared, then multiply by delta t, so it matches the form. Now we can convert this into an integral. And here, if you look at this integrand with the term xi plus 1 minus xi over delta t, it looks like a derivative. We can denote this as x dot. So the integrand will just be x dot square. Then we have the integral from 0 to t, x dot square dt. So this is the equation for the probability of a path, also known as the path integral. And for the path integral formula, we can denote the exponents as I of x. That equals to a half and integral over 0 to t x dot square dt. This is called the action. So the probability of the path is given by the exponential of minus action. Now this is a very neat formula, except there's one problem, which is the x dot. The time derivative of the Brownian motion can be problematic. This is because the Brownian motion is not differentiable. So let's take a closer look. Basically, the x dot is defined as delta xi over delta t. And with Brownian motion, we know that delta xi is normally distributed with mean 0 and variance delta t. Then for the distribution of x dot, that will be normally distributed with mean 0 and variance 1 over delta t. This is because the property of the variance. So the variance of delta xi over delta t equals to 1 over delta t squared times the variance of delta xi. And that equals to 1 over delta t. So now we see the issue here. When delta t is very small, this variance blows up to infinity. This is problematic because for a properly defined derivative, it needs to converge to a finite number. But this is not the case for the Brownian motion. And because this x dot goes to infinity, it means that the action also goes to infinity. So this just means the probability of the path equals to 0 as n goes to infinity. Okay, even though this is kind of a problem for the path integral, but it does make sense. Because if you think about the process, when we generate a path, we need to sample infinite number of Gaussian distribution. So this probability density is smaller than 1. And when we take the product of it, that must be 0 as n goes to infinity. Also, just intuitively, it makes sense that in the continuous time, the probability of observing one exact path is 0. And this is an important fact we need to keep in mind. It means the path integral here cannot be literally interpreted as assigning probability to the path. And the rigorous understanding of the path integral requires measure theory and the Wiener measure, which we will not be discussing in here. But conceptually, the stochastic simulation is a correct idea to keep in mind. So the main point is that we can still generate many paths from which we can estimate quantities such as averages. So the path integral is really defined as an infinite limit for the stochastic simulation. And in fact, in here, let's also look at the path integral of the expectations. We can derive that from the path integral of the probability. This is perhaps a more common path integral formula that we will see, especially in physics. Okay, so let me just clear up the space. So let's say that we want to compute the expectation of some function depends on the path. And let's define that as v of path. This can be the return of a stock trading strategy. So this expectation equals to v times the probability of the path. Then we need to sum over all the paths as d path. Okay, so this is the same expectation formula, except that the probability distribution is defined over the path. Okay, but now we need to translate this into proper math equation. So let's just think, what is d path? The idea here is still we can use a finite approximation. So let's say that we have a stochastic path that we sampled in the finite space. Then it reduces to a multivariate distribution. So it's basically a joint distribution from x1, x2 to xn. Now, if we are living in the continuous time, we just need to consider the case of n goes to infinity. So this integral will just equals to the limit of n goes to infinity. Then we have dx1, dx2, all the way to dxn times v of x times p of x. So I'm using x here to denote the path. And for the path integral formulation, it's common to write the differential in the front. Then a common notation for the path integral is that we can replace this part with the capital dx. And that followed by v of x. Then for the probability, we can replace that with the exponential to the minus action. Okay, now this is the expression for the path integral of the expectation for v of x. So this basically has the same form as the famous Feynman path integral in quantum mechanics. But that will have a different action function comparing to the stochastic process version given by the Brownian motion. Okay, good. Now we derive these very cool looking path integral formulas. But my take is that in practice, the path integrals are often evaluated through Monte Carlo simulations rather than analytically evaluated using these formulas. But these formulas really give us a very nice framework to think that the stochastic processes is really about the distribution over the path. And in order to sharpen our understanding on how to use the distribution of path, let's look at the example of the first passage time. So the first passage time of the Brownian motion doesn't really require the path integral to solve, but the idea behind it requires us to think using the probability of the path, not just the density function from the PDE. Okay, so for the problem setup is that suppose we are given the Brownian motion and we are given certain position value A. Then the question is, what is the distribution of time for the process to reach A for the first time? Okay, so now let's think about how we can formulate this probability into equations. So first, let's define capital T to be the random variable of the first passage time. So we can define the probability distribution using its CDF. So that is given by the probability of capital T smaller or equal to small t. What this means is that suppose our small t is somewhere in here, then this CDF is saying that what is the probability of the path passing through the threshold A before the time small t. So on the path level, this is equivalent to the number of paths whose max value goes beyond the threshold A. So that's called the max value MT. We can write that as the Brownian motion, let's say B of S, with M smaller or equal than T. So if the first passage time to A is smaller than small t, then the process must reach beyond the threshold A before the time t. Okay, but before we continue, let's just take a moment to look at this equation here. The important thing is that let's not take this equation too literally, because there are two problems with it. So first, we need to consider the probability of each path. We can use the path integral to find its probability, but that will collapse to 0. And second, it doesn't really make sense to count the number of paths because there are uncountably infinite number of paths in the stochastic process. So basically, people from measure theory will shake their head looking at the equation that I wrote. And perhaps a better way to think of it is that these paths are sampled from the stochastic simulation. So with finite approximation, we can write that as a ratio between the number of paths. But for the continuous time stochastic process, we cannot take this too literally. It's mostly just for the argument's sake. Okay, so the next idea is really the key to solve the first passage time problem. It's called the reflection principle. So the key idea is that if we consider all the paths whose max value is greater than A, we can break that down into two scenarios. And let me just draw you a picture. So these two scenarios can be divided by the value at the time small t. So in the case 1, the process value exceed A, then drop back down. So basically, this is a case consists of the path whose max value is greater or equal to A, but the terminal value Bt is smaller than A. Then for the second case, we just have the terminal value greater than A. So here's the time small t, and here's the A. Then we have the maximum value greater than A. and the process value is also greater than A. So the reflection principle is saying that these two scenarios has the same probability. Basically, it means that the path has a one-to-one correspondence. So basically, if we take a path from the first case, we can just reflect this part of the path along the threshold A to the other side. And these two paths will have the exact same probability because of the symmetry of the Brownian motion. So basically, for each path we found in the case 1, we can just reflect part of the path to find its twin in the second case. It just means that the number of the paths in the first case equals to the number of paths in the second case. Okay, so how do we use this fact? It turns out we only need to take a closer look at the second case. If the Brownian motion has the terminal value greater or equals to A, it means that the maximum value must be greater or equal to A. So it turns out that this max condition doesn't even need to be included. So this just equals to the number of the path whose terminal value BT is greater or equal to A, right? It just means the terminal value BT is higher than A, the maximum is also going to be higher than A. Okay, so from the reflection principle, we can just basically write the probability of the first passage time equals to 2 times the number of paths with value BT greater or equal to A over the number of all paths. Okay, so now this is a nice equation because it reduces to the marginal distribution. Now all we need is to consider the value at BT. So that will just equals to 2 times the probability of BT greater or equal to A. And we have a formula for this probability because the distribution is Brownian motion. So this just equals to the CDF of the Gaussian distribution. So that is given by 2 times 1 minus the Gaussian CDF of 1 over the square root of t. Then for the probability density function, the PDF, we can just find the derivative of this function. So I'm not going to do that in here, but this actually has a closed form. And the solution is called a Lévy distribution. So a very mind-blowing fact about the Lévy distribution is that the expectation of the first passage time is infinity. So basically, the Lévy distribution is very heavy tail, and the expectation of the passage time is not finite. And another very surprising fact about Brownian motion is that it almost surely reaches the threshold eventually, but the expected passage time is still infinite. So from a stock trading perspective, just because the stock price is random, it does not guarantee you that it will reach the target price within a reasonable amount of time. Okay, so that's about this video. We peek through the curtain of the path integral and look at the stochastic process from a different perspective. We see that it is not just a distribution at fixed times, but a probability distribution over the entire path. And at the same time, the path integral also teaches us something important about stochastic processes. In the continuous time, a single exact path has a probability 0. And to make these ideas mathematically rigorous, we need to formulate with measure theory. So Wiener measure, namely, Even though the mathematical foundations of the path integrals are subtle, but the viewpoint is extremely powerful because the stochastic processes become more intuitive at the path level rather than only through the PDEs. For many real-world applications, the Monte Carlo simulation is often used to evaluate the path integrals. And when we simulate random trajectories, we are already working with the idea of the probability over the random path.